Okay, so let me begin. Okay. So someone asked me for some references, so I'll just write down the archive number of 2 reviews that I had written at various times. Because the most of what I am going to discuss here can be found in these reviews. That is you will find references to in these reviews which will have that material. So yesterday I described a specific example of a system, okay, just a string wound around a circle, okay, and I discussed how that can be thought of as a collection of harmonic oscillators, and then how you can go ahead and try to count the number of states. So today I will start with a more general case, okay, without referring to any specific system. So a general case is that we have infinite number of harmonic oscillators, which was the case last time also. And the ith oscillator carries charge and in units of minimum charge. So let me remind you the situation that we had. We said that we consider a black hole which carries say k charges, and we are interested in counting the total number of states up to this sign, which I'll remind you later. We are trying to count the total number of states, okay, extremal black hole states of charge that is n1 q1 naught n2 q2 naught up to nk qk naught. So here the naught corresponds to minimal unit of charges. These are the minimal unit of charge. And these are some large integers. Okay, so you want to count total number of states of this kind, and what I am saying is that the quantum system that you have to deal with typically consists of infinite number of harmonic oscillators, and the ith harmonic oscillator carries these many units of charge for each of those k charges. So a general state will be given by product over I, ai dagger to the power ri on the vacuum, where ri's are integers. From 0 to infinity. And the charge that such a state will carry will be the first charge. See, ai dagger carries the first charge in one I. Okay, this is an integer. These are all integers because we are using minimal unit of charge. These are measured in units of minimal unit of charge. So these are integers. Or maybe I can just put the charge unit anyway. Let me write this. N1 Q1 naught. So this will carry charge that is given by sum over I Ri N 1I is clear? Because Rth oscillator, each of these I daggers carry this much charge. If you apply it Ri times, it will carry Ri times this much charge, right? And then you have to sum over I. And you do this for every charge. And this you want to be equal to N1 Q1 naught, N2 Q2 naught, up to Nk Qk naught. Okay, because we are looking for a state that carries this much charge. So by comparing the two sides, we will see that N1 is sum over I Ri N1I Is this clear? So the question is, how many ways can we choose Ri's such that we satisfy this relation? So you can write this as sum R1 equal to 0 to infinity, sum R2 equal to 0 to infinity, the infinite number of them, and then we write delta of sum over I Ri N1I N1 delta So these are Kronecker delta functions, which tells us that it vanishes unless these two are equal. So what we are doing is that we are simply summing over all possible choices of the Ri's, right? So R1 goes from 0 to infinity, R2 goes from 0 to infinity, similarly R infinity goes from 0 to infinity. The summand is 1, right? So this will give infinite answer, okay, if you don't put any more constant. But now you are multiplying it by these delta functions, which tells us that it will give you 1 only when this condition is satisfied and this condition is satisfied, and similarly the kth condition is satisfied. Delta sum over I Ri Nki is Nk. Okay, so this is just a formal way of writing exactly this. How many ways can we choose the Ri's so that this condition is satisfied? Is this clear? Okay, that if you count 1 every time this condition is satisfied, that means you are counting the number of times you can satisfy this. Okay. So this looks like a complicated problem, right? You have to solve these constraints and see how many times you can solve these constraints. But like last time, we saw that it is easier to deal with the partition function. Okay, so let me write the partition function. F Q1 to Qn. The definition of F, this is sum over N1, N2, Nk omega N1 to Nk. So I should have written this is this visible? Okay.
Iterator here.
At this level it is okay? Okay, so below this I shouldn't go. Is that okay? Fine. I'll keep it like this. Okay, I guess here also is the same, right? Okay, so this is defined as this times Q1 to the N1, Q2 to the N2, up to Qk to the Nk. Right, this is a definition of partition function. Okay, because if we have this, if you know F, then by Taylor series expansion, we can read out what the omegas are. So I am now going to substitute this expression for omega that I have written here in this expression. So this gives you F Q1 to Qk as sum over N1, N2 up to Nk. This quantity over here, this multiple sums. Okay, I will write formally as a product. I will write this as sum product over I equal to 1 to infinity, sum over I Ri. Sorry, sum over Ri. Okay, so this basically means this. Okay, that you have to take the sum over I, sum over Ri for every I. So let me write it that way. So product over I equal to 1 to infinity, sum over I, sum over Ri. Okay. And then those delta functions, delta and now the idea is that we do this sum first. Oh, I forgot the Q's. Yeah, right. So all I did is that I wrote this sum over N1, N2, N3, Nk omega, and I used this expression for omega. Okay. And then I multiplied by Q1 to the N1 to Qk to the Nk. Okay. And so now the idea is that we will do these sums first, because what these sums will do is that it will simply set N1 equal to sum over I Ri N1I, right, because it vanishes unless N1 is equal to this. Similarly, N2 should be sum over I Ri N2I, and up to Nk is equal to sum over I Ri Nki. So this then can be written as product I equal to 1 to infinity sum over Ri, and then Q1 to the power sum over I Ri N1I up to Qk Is this clear? Yes. So let me remind you, physically what we are doing is that these are the charges carried by individual oscillators, right? For oscillator number I carries the charge N1I for the first charge, N2I for the second charge, and Nki for up to the kth charge. Okay. So here you have to get used to the fact that instead of having just one electric charge, there are k electric charges, right? And each oscillator can carry different amounts of electric charge, right? The first oscillator, okay, according to this, is carrying N11 amount units of electric charge for the first electric charge, N21 of the second electric charge, and so on. Right? That's the convention. So we have this, okay, then nothing else is needed because we did the sums. So this I can now write. Here we go. The two steps. So this one I am going to write as Q1 to the power N1I is this clear what I have done here, right? Because you see when you raise it to Ri's power, right, each N1I will get multiplied by Ri, right? So you get N1I Ri, N2I Ri, and so on. And then the product can be written as a sum in the exponent, right? Q to the A times Q to the B is Q to the A plus B, right? So here you had a sum over I in the exponent, but now I am writing this as a product over I. So this, in one more step, I can just rewrite this as product over I equal to 1 to infinity, right? See here there's a separate product over the sums and then a separate product over the summand, but now I can write it as a single product Ri equal to 0 to infinity. And this becomes product I equal to 1 to infinity 1 minus this clear? See, this is here I have used the fact that sum over R equal to 0 to infinity x to the power R is 1 minus x inverse. Just the expansion of 1 minus x inverse is this, right? So I have here you have an expansion of that kind. So I can write this as 1 minus this inverse. So this basically says that if you know the what kind of oscillators are there and what charges they carry, right, then we can directly write down an expression for the partition function using this formula, right? Because this only needs to know for each I what are the charges that it is carrying. Is this clear? Right. In yesterday's example, we saw that there are oscillators that are carrying different amounts of charges, right? Because the one oscillator is carrying momentum 1 over R, another oscillator is carrying momentum 2 over R, another carrying 3 over R, and so on. And so you got the product over such oscillators, right? This is just generalization of that statement. Okay. So later on, I'll show you some formulae without deriving it, right? But essentially, all those formulae would have a structure like this. Okay. And if we just look at this formula, we can figure out what kind of oscillators were there of what charge, right? Because the final formula will have exactly this kind of expression, right? And the derivation of this formula will basically follow this procedure, right? That we identify what kind of oscillators are there in this as constituents, what charges they carry, and then just apply this formula. Are there questions on this? She. Now, if you recall, we are dealing with theory with fermions. So, if you have theory with fermions, they are not only bosonic oscillators, but they are also fermionic oscillators. So, fermionic oscillators are very similar to bosonic operators, except that instead of commutation relation, we have anti-commutation relation. So, fermionic oscillators they are like harmonic oscillators. Their creation and annihilation operators are B dagger B. And we have anti-commutation relation B B dagger equal to 1 and B B is 1 is 0 and B dagger is 0. Okay, this is just like the bosonic harmonic oscillator, except that all the commutators are replaced by anti-commutators. Okay. So, this in particular says that B square is 0 and B dagger square is 0. And this you might have been might have seen in your quantum field theory course. So, on the quantized fermions, right, you get the creation and annihilation operators, but they square to 0, right? You cannot apply more than one creation operator, and that's essentially the reason for Pauli exclusion principle, that you cannot put more than one formula in a given state. So, if we can repeat exactly the same analysis, so let me just change the notation a bit. So, suppose we have the ith fermionic oscillator carries charge Okay, there are several levels here which you shouldn't be confused about, right? This level, the lower level 1, 2 up to k levels, how many different kinds of charges you have, right? If you have a single electromagnetic field, then this k will be just 1. Okay? And this I level is the oscillator level, right? And that's typically infinite. There are a typically infinite number of harmonic oscillators. As we saw last time, even a single string has infinite number of oscillators. So, now the analysis will be very similar to what I did here. The only difference will be that this occupancy number, right? So, the general state, let me write this general state. So, the state will have the structure product over I, AI dagger to the power SI on the vacuum, where SIs can take value 0 or 1. Okay, that's the main difference between fermionic and bosonic oscillators. It cannot take more than 1 because AI dagger square is 0. And the charge that it carries Yeah. So you can tell me whether it's harmonic. Assume that the vacuum is bosonic, right? So what kind of a state will this be? Harmonic or bosonic? Bosonic? Yeah, dagger is a harmonic operator. This information will be needed, right? So let's try to fix it. Whether it's harmonic or bosonic state. Assuming that the vacuum is bosonic. Harmonic. Ion dagger and vacuum. Is it a harmonic state or bosonic state? If the vacuum is harmonic, if the vacuum is bosonic, ion dagger on the vacuum. Think physically in terms of field theory, right? Ion dagger on vacuum means what? Well, ion dagger on vacuum creates one fermion out of vacuum, on the vacuum, right? So the state is fermionic, right? Ion dagger on the vacuum is a one fermion state. Is that clear? Just think of the quantum field theory, right? If you have a free fermion, if you apply its creation operator on the vacuum, it's a state with one fermion. Ion dagger, A2 dagger on the vacuum. Is it fermionic or bosonic? It is one fermion in state 1, another fermion in state 2. So, as a overall state, is it bosonic or fermionic? Hydrogen atom. Okay, hydrogen atom is fermionic or bosonic? Fermionic. What is hydrogen atom made of? Yeah, it has a proton and an electron, right? So is it a bosonic or fermionic? Yeah, but that's only electron spin. I'm asking about the hydrogen atom as a whole. There is bosonic, right? Because a proton is fermionic, right? So if you put two fermions together, you get a bosonic state, right? So A1 dagger, A2 dagger on the vacuum, is it fermionic or bosonic? It's a bosonic state, right? A1 dagger, A2 dagger, A3 dagger and vacuum. Fermionic, right? So what determines if it's fermionic or bosonic? Pardon? Yeah. So whether this is odd or even, sum over I SI, right, equal to odd is fermionic, and sum over I SI is even is bosonic state. Okay, this will be important because if you want to calculate the index, if you remember, index is defined as something which gets positive contribution from bosonic states and negative contribution from fermionic states, right? So it will be important when you calculate the index. Okay, but first let's just calculate the degeneracy. So A dagger is fermionic creation operator, right? That's the meaning of saying that it's a fermionic oscillator, right? So A dagger is fermionic creation operator. Is this okay? Okay, so now we just repeat this calculation. Okay, all that changes is R is replaced by S and N is replaced by M. And the sum over R, here the sum over R was running from 0 to infinity. Now the sum over S will run from 0 to 1, right? Because occupancy number of a fermionic cannot be more than 1, right? That's going to be the only difference. So you can just take the bosonic answer and read out for the fermionic answer. Okay. So I'll do it for the final F. Okay. So at this stage, right, this was the bosonic partition function. If you replace it by fermion, the n's will be replaced by m's because fermionic oscillators may carry different charges, and this sum over r I equal to 0 to infinity will be replaced by sum over si equal to 0 to 1. So, fermionic contribution to a partition function is product I equal to 1 to infinity sum over Si equal to 0 to 1 which I can just write as product I equal to 1 to infinity sum Si equal to 0 to, sorry, sum we don't write, I will just write this as 1 Si equal to 0, it gives you 1, and then Q1 to the M1i up to Qk to the power mki. So, compared to the bosonic result, we see that this inverse is not there anymore, right, because the sum does not run all that from 0 to infinity, it runs only from 0 to 1, and this minus sign is also not there. Okay, because minus sign came because if you expand 1 minus x inverse, you get only positive coefficient, right. That is why the 1 minus x inverse came. But this counts the degeneration. This is the partition function associated with degeneration. But we had said yesterday that the quantity that really remains unchanged as you change the moduli is not the degeneracy, but the index. So, what is the index? Index is the number of bosonic states minus number of harmonic states. Right? So, you should really count that, not number of just the number of states. Right? This one is not taking into account whether the state is bosonic or fermionic, right? It is just counting it. Is this point clear? Right? These are total, yes. Yes, yes. In the last lecture, we didn't have any fermionic oscillator, right? But I said when I discussed the various subtleties, one of the subtleties was that what remains unchanged is not the total degeneracy, but the difference between the number of bosonic states minus number of fermionic states, right? So that's what you should really try to count, right? And this counting is giving just the total number of states coming from the fermionic oscillators, right? Yeah. So in the last lecture, we didn't have any fermionic oscillator, so this question didn't arise. That is on the black hole side. This is, we are doing here the quantum mechanical side, right? Here it's not true that all the microstates are bosonic. By the time you have gone to the other corner of the moduli space where you have found a black hole, there you can show that all the states are bosonic. Okay, but not when you are doing the quantum counting. So, what should we do to repair this, right? Suppose you want to really count the number of fermions minus number of bosons, right? What will change? So, the state we have to put a weight factor to the state, right? Whether the state contributes positively or negatively. Right? So, what is the weight factor you should put? We just discussed it a few minutes ago, right? It's supposed to be minus for the fermion and plus for the boson. Signature, right? So, what is the expression? Can you see from this what we should put? See, sum over Si equal to odd gives fermions and sum over Si equal to even gives bosons, right? So, what combination will have the property that it's minus 1 to the power sum over ISI, right? Because minus 1 to the power sum over ISI will be minus 1 for fermions and plus 1 for bosons. Is that clear? Right? So, to count index, so for index, we have to put a minus 1 to the SI, right? That's the only difference. So, I equal to 1 to infinity, some Si equal to 0 to 1, Q1 to the M1I. I am not writing the sum over ISI because there is already a product sitting outside, right. This product, when you take it here, it will become minus 1 to the power sum over ISI, right. So, I am using that minus 1 to the power sum over ISI is product over I minus 1 to the power SI, right. And in this expression, there is already a product over I. Okay, so I just write it as minus 1 to the power SI. Okay. So, this is product I equal to 1 to infinity 1 minus is this clear? Okay. So, this now looks even more similar to the expression that we had for bosons, right. This minus sign is there here also, except that here there is a minus 1 and here it is a plus 1. Okay. So, this means that if we have a bosonic oscillator and a fermionic oscillator carrying exactly the same charges, their contribution will just cancel, right. Because finally, when we want to calculate the full partition function, right, full index, you have to take the contribution from bosonic oscillators and fermionic oscillators, right. So, we will take the product of this and this. And now you see that if you have a bosonic oscillator and a fermionic oscillator with identical charges, here you get inverse of this expression, there you get just this expression in the product. So, in the product you will just cancel, right. And this is essentially the effect of supersymmetry, that if you have equal the bosonic and fermionic oscillators carrying equal charge, then they do not contribute to the index. Okay. Fortunately, the kind of black holes that we will be discussing, it will not cancel exactly, right. Some bosons may cancel some fermions, but there will be some left over, because if it cancelled exactly, then you will not get any degeneracy, right. It will basically say the index is 0 for all states, right. That certainly is something we do not want. Okay. So, I will give examples of partition functions that you actually get from a computing index. Are there questions? Okay. But before I give the example, let me describe how we can actually extract the degeneracy out of partition function. So, suppose we have calculated omega, sorry, not omega, f. So, f is much easier to calculate. Okay. And f is related to omega by this expansion. So, the question is, And here from now on, I will only talk about the index, right? I am assuming that this f is such that we are actually calculating the index, right? Which means that we have already put the minus sign that is needed for the harmonic oscillators. So the question is, given f, how do you calculate omega? Now, if you are interested in omega for small values of n1, n2, etc., then what we can do is that we can take the expression for f and that's your Taylor series expansion, right? We just pick a Taylor series expansion in the q1, q2 up to qa, qk and pick up the appropriate coefficient. Okay, suppose you want to know the you need to want you want the answer for all the n's are 2. Then you do a Taylor series expansion up to order q1 square, q2 square, qk square and pick up the coefficient of the Taylor series expansion. And ifs are known explicitly enough so that you can do that, right? When I give the example of f, we'll see that what kind of structure f has. Okay, you can if you want to do Taylor series expansion, the expressions for these partition functions are known to sufficient degree that you can actually do the Taylor series expansion. But our goal is to try to extract the omega that we can compare to the black hole entropy, right? Log omega with black hole entropy. And in order to have a black hole, we need n to be large, right? At least one or multiple n's should be large if we want to think, if we want a state which in some point in the moduli space will actually be described by black hole, right? Which means whose Schwarzschild radius will be larger than the compound radius. Okay, that 1 over n. So for extracting the expression for omega for large n, it's not efficient to Taylor series expand f. Right? Imagine that you want it for n for a million. Right? Then you have to do Taylor series expansion to order q to the 1 million. Right? That's very inefficient. You can do it on a computer if necessary, but a more efficient way would be to see if there is a way to extract f differently. If they are able to extract omega differently, right? Which is efficient for large n, but may not be efficient for small n, right? Because large n is what you need for black holes. Okay. So I'll describe the general method that one uses for these partials, right? How to extract the expression for omega for large n's. So for that we try to regard this as a Fourier expansion. Okay. So let's define tau 1 to tau k such that q1 to 2 pi I tau 1 or maybe I should have said one more thing which I didn't do. Okay, let me say that first, then I'll come back to this. Okay. That we saw that the index is given by products of terms like this, right? Either this or inverse of this. Okay, inverse from the bosons and this from the fermions. Okay. But sometimes there may be also additional contribution, which can be thought of as coming from what we will call the 0-point charge of the vacuum. So if you recall, okay, let's look at this state over here. So the charge carried by this state, right? We wrote down an expression for the charge carried by this state, which is the charge that comes from the oscillators. But we assume that the vacuum doesn't carry any charge, right? Because we only added up the charges that the oscillators carry, right? We didn't count if there is any charge that the vacuum can carry. And the vacuum can sometimes carry charge, just like we know that the vacuums can sometimes carry energy, right? Harmonic oscillator, downstate energy is not zero, right? It's half h bar omega. Right? So the same principle when we apply to charge, right? Because of the normal ordering issues, one finds that sometimes a vacuum may also carry charge. and that gives an additional contribution to the this f, right, the partition function. Okay. So, the contribution from charge of the vacuum charge of the vacuum is Q1 to the C1, Q2 to the C2 up to Qk to the Ck if 0 carries charge C1 to Ck. Okay, so this will be an extra factor that comes in the expression for the partition function. Okay, just if the vacuum carries some charge. Yeah, that is true, but that you subtract out if there is a normal ordering, right? But after the normal ordering, there may still be some charge left over, right? And that's what you count. Right? See, this is not the vacuum. Okay, let me say it this way. This is not the vacuum of the whole theory, right? Here, by vacuum, I mean that the system of a quantum mechanical system, right? And you are trying to calculate the charge of that quantum mechanical system, right? I think what you are thinking of is a vacuum like the Dirac sea, right? That, of course, yes, we assume that the vacuum, the true vacuum where there is no state, has no charge, right? But here you are talking about a black hole state, right? And the ground state that you are talking about is the ground state of the black hole, right? So this 0 refers to the ground state of the black hole, right? Not the ground state of the quantum field theory or string theory, right? And that could carry some charge, right? Which in principle can be calculated, right? So you calculate these charges C1, C2 up to Ck, and then that gives this additive, the extra multiplicative factor in the partition function. Okay. So the partition functions are products of terms like this, inverses of this from the bosonic oscillator, and there is an overall factor of this kind. Is this clear? Are there questions? Okay. So we introduce these variables. And then we can rewrite this as a Fourier expansion. If you introduce these variables, then this becomes like a Fourier expansion. So you can write that expansion as f q1 qk right. All I have done is that I have just replaced the qi's by e to the 2 pi I tau i's. And now you see that this looks like a Fourier expansion in multiple variables, right? Because since n's are integers, this is periodic in tau 1 with period 1, periodic in tau 2 with period 1, and so on. Okay, so this is exactly what we call a Fourier expansion. And if you have a Fourier expansion, then of course you also know how to invert it. Okay. So omega n1 to nk can be written as an integral d tau 1 Is this clear? Right, this is an inverse Fourier transform. Right, if a function has Fourier expansion like this, This you are familiar with. The f of x is sum over n to the 2 pi I nx gn. This implies that gn is integral 0 to 1 dx to the minus 2 pi I nx f of x. This is familiar to everyone, right? If you have a Fourier expansion like this, you can invert the Fourier expansion, right? G of n in terms of f of x. This is just the same thing, except that I have applied it many times, right? K times. Okay, otherwise it's just the inverse Fourier transform. Yes, yes. Yeah, but the full expression will have the products of everything. Yes, but it has bosonic states. Yes. So we don't have to separate. Ultimately, you have to put them together, right? But we treat each oscillator separately. Why is the bosonic? See, harmonic contribution has both bosonic and harmonic part, right? But whether it is bosonic or harmonic depends on whether sum over I SI is even or odd, right? Otherwise, it has both bosonic states and harmonic states. Right? Then we said that if in the index we are supposed to use an extra minus sign if the state is harmonic, right? So that's why you put this minus one to the sum over I SI. Right? Once you do that, this is the contribution to the index from the harmonic oscillators. Right? But in a given system, there are both harmonic oscillators and bosonic oscillators. Right? So if you want to calculate the total contribution to the index, right, you have to take a contribution both from the harmonic oscillator and the bosonic oscillator. Right? And this totality of the collection of all the oscillators will create some states which are bosons, some states which are fermions. Right? However many times you apply a bosonic oscillator, you don't change the statistics. But every time you apply a harmonic oscillator, you change it from bosons to fermions and vice versa. And then in this whole thing, we are counting the index, which means we weight the harmonic states by -1 and just simply sum over all states. Right? That's what we are doing here. And I'm not sure if I got the question correctly. Is it okay? Or so basically, we are counting everything together, right? The only difference is that we are putting an extra minus sign if the state is harmonic. Right? Otherwise, we are democratically summing over harmonic states and bosonic states. Pardon? No, in this case, it's not. We have forgotten about oscillators, right? We have already gotten the oscillators, everything to get the partition function, right? Now we have the expression, right? Forget about where it came from, right? The oscillators are gone. We have to analyze this expression and see how it grows for large n, right? These n's. Maybe if I had put this capital N, it should have been a little easier. So this n is the analog of the capital N. So I just wrote this because this may be more familiar to you instead of the Fourier transform in multiple variables. Right? But this is the Fourier transform in one variable. Right? This is just a generalization of that Fourier transform in multiple variables. Right? So now I am not talking about the oscillators anymore. Oscillators have been used to calculate f, and now I am asking that given f, how to extract omega. Right? In particular for large f. Is this clear? Okay, so we have an expression like this, okay, but there is some subtlety in that expression, which I will mention. So, here you notice that I have not written the range of integral. But if you compare with this, we would think that the ranges of integral over each of the taus should be from 0 to 1. Right? Because it's periodic with period 1, right? You see integrate from 0 to 1. But there is a problem of integrating from 0 to 1, and that is the following. That you recall the definition of f, which is here. And for black holes, we are looking for systems which are like black hole, which will eventually produce a black hole degeneration. And for black holes, we know that omega actually becomes large for large n, right? Omega grows. So, for black hole system, we expect omega to grow for large n. In fact, it often grows exponentially, right? Exponential of root n is what we had seen last time, okay, even for that simple system. Okay, and I said that growth was not big enough for black holes. But typically, we expect that the kind of system that you are looking at, omega will become large for large n. If it becomes large for large n, then this expansion that we have here, we expect that this will not be well defined when tau i's are real. Why? Because these are just phases, right? When taus become real, then these are just some phases, right? So, as you are summing over n, this is growing exponentially, right? And there are some phases. So, this expression becomes ill defined, right? It's for absolutely convergent, right? Absolute convergence means magnitude should go down, right? Okay, here certainly the magnitude doesn't go down because magnitude of this will be 1, right? And this magnitude is growing. So, what one has to do is to try to define this in some part of the complex tau plane where this expansion is convergent. Okay. So, f of q1 to qn or q1 to qk is well defined for imaginary tau I large for every I. Because if imaginary tau I is large, right, then these will be exponentially suppressed. Right? I times I is -1, right? So, imagine tau 1 is equal to I lambda 1, right? Then this will be like e to the minus lambda 1 n 1, right? That falls off. Okay, so this can compensate for the growth of omega. So, for this reason, we are going to take we will assume that the f is well defined, not on the real axis, not necessarily on the real axis, but in some part of the complex plane where the imaginary parts of the tau are large. Is this clear? So, then this integral I write from I lambda 1 to I lambda 1 plus 1, I lambda k to I lambda k plus 1, where lambda k's are large positive number.
It is being very large.
Okay, if imagine that the tau 1 is I lambda 1 plus x, right, and you are integrating from x equal to 0 to 1. Okay, that is what this means, right? I lambda 1 to I lambda 1 plus 1 means that you are integrating from, you write tau 1 equal to I lambda 1 plus x and integrate x from 0 to 1. So, if you write tau equal to I lambda 1 plus x, then this expansion e to the 2 pi I tau 1 n 1 becomes e to the power minus 2 pi lambda 1 n 1 times e to the 2 pi I n 1 x. Now, if lambda 1 is large, then this is small, right, for large n. because this is falling off exponentially, right? It will be minus a large number is small. Right? So if lambda 1 is large, then for large n it is suppressed, and hence this sum that you see here will converge. Is this clear? Because in order for this to converge, you have to make sure that the summand falls off, right, for large n, because you are summing over n all the way to infinity. And in order that the summand falls off, you have to make sure that the summand is small, right? And that can be achieved by taking tau 1 to have a large imaginary part. Right? Similarly, tau 2 to have a large imaginary part. Then the n2 dependent part will fall off, and so on. Is of
It is not necessary the construction to for tau i's to be uptake because no that
no, we don't know. Oh, Q1s are arbitrary complex variables, right? I have never said Q1s are real. No. Q1, sorry, I think Q1s are not charges. Q1s are the parameters. Say Q1 naught where the Qi naughts were the charges. These were the charges. Maybe I should have used a different variable. This came from the definition of the, see, this Q's came because I defined f Q1 to Qn as sum over n1 to nk, omega n1 to nk, Q1 to the n1 up to Qk to the nk. Right? This is just arbitrary complex variables, right? We define this for arbitrary complex variables. Right? So these Qi's are not charges. Yeah, I mean, this is the definition of this is the way I introduced f, right? And if I want to think of f as a function of some complex variables, I can take Q's to be complex, right? The right hand side is well defined. So the only place where you have to worry is that this sum should be convergent, right? So it may not be defined everywhere in the complex plane, right? But in some region of the complex plane where the sum is convergent, we can define this. Okay. So if this is confusing you, just change Q's to some other symbol, right? These Q's are not charges. Okay, the charge units, we introduce small q for charge unit, which are the Qi0. These Q's are completely, these are just arbitrary complex variables, right? In terms of which I have introduced this partition function. Yes.
find out the
You have to find omegas, yes.
why didn't he just check the of f in terms of
Yeah, but if you are doing it for million, right? You have referenced a million times. Right? We are really trying to find a large n behavior of these omegas. Yeah, that's the reason. Yeah, otherwise, I mean, these are Taylor series expansion. In principle, if you have a computer, right, you can feed this f in the computer and ask it to Taylor series expand, right, to the arbitrary order. But that's not a very efficient process, right? So we are trying to see what is the efficient way of extracting the large n behavior of these omegas. Is that clear? Okay, are there questions? Pardon? Yeah, that's true, but the point is you don't have to even differentiate it, right? If you put it in Mathematica, a function, and ask it to Taylor series expand, it will do it, right? It may not be able to do it up to million, but up to 20, 30, it will certainly do. Right? So the problem is not that you cannot get for low values of n, right? But we are trying to find the large n behavior because that's where the black hole is, right? The black hole, this can be described as a black hole only when the n's are very large. Right? The number of units of charge that it carries is very large, and for that, this Taylor series expansion, right, is not very efficient. Okay, so let me write this again. Again, I'm emphasizing that these Q's have nothing to do with charges, right? These are what are called the fugacities. Right? These are the ones that are used, that there are some auxiliary variables, right, which have used to define the partition function. No, they are independent variables, sorry, tau1 plus x1. So let me write this again. So you have omega n1 to nk as integral this is still not enough. This is just rewriting the original formula. But what one can show is that once you have written this as an integral, you can evaluate this integral using saddle point approximation. Okay, that relies on knowing the properties of f. Right, this function f often has nice properties. Right, that allows you to evaluate this integral. Okay, at least for large n using saddle point method. Okay, so we evaluate this using saddle point method. Okay, and this is what is able to extract the behavior of omega for large n, right, which is what I need to compare the black hole entropy. Yes, you have to look at you have to pick up the saddle point to the maximum contribution, right? So there are multiple. You mean there can be whether there can be multiple saddle points, right? Yeah, so that can be, but typically they have different weights, right? So you just pick the saddle point that gives the maximum contribution because you are looking at the large behavior for large n, right? And then other contributions are exponentially suppressed compared to the largest one. So now I'm going to give you some results. So you have seen some aspect of string theory, right? At least string theory in 10 dimensions and some compactification. So you are going to take what is known as heterotic string theory. String theory in D equal to 10 and compactify six directions on surface. So you take xm as xm plus 2 pi rm, okay, which means that if you translate xm by 2 pi rm, we'll come back to the original point. That's what a circle of radius rm does. And we take this for m equal to 4 to 9. And x mu for mu equal to 0, 1, 2, 3 are non-compact directions. So these are 4-dimensional theory. Now in D equal to 10, we have massless fields as GMN, BMN, phi. Right? And then there are some other gauge fields which I will not write down because you may not have seen it. The massless fields. Right? Here m and n run from 0 to 9. This you have seen. Right? These are even in bosonic string theory, right? So this part is common to all string theory. So I mean we can start with that. Right? The other massless fields which you don't have to worry about right now. So once you compactify, right, then G M mu and B M mu, what kind of fields are these? These are vector fields, right? Because these have an internal index, right, M, which runs from 4 to 9, right? But these are like scalar directions from the 3 plus 1 dimensional viewpoint. And the mu index is a vector index. Okay. So then in this theory, we can consider states that are charged under these vectors. Right? We can consider black holes which carry charges under these vectors. And we will focus on a class of black holes that carries charge only under some of these vectors, right? Not all of these vectors. And it can carry both electric charge and magnetic charge under these vectors. Here you are going to consider a special class of states. So I give some arbitrary charges. Now they will look ad hoc and they are indeed ad hoc. So the point is, how do you decide what kind of charges you should choose? Right? And this is decided just by practical considerations. That you should choose the charges in such a way that at some point in the moduli space you get a black hole. Okay, because you have to make sure that at some point the horizon radius is large enough compared to the component radius, so you should get a black hole. Right? That is the first criteria, because if you are going to study black hole. The second criteria is that at some other point in the moduli space, we should be able to curve states. We should be able to describe this as weakly interacting quantum system and count states. And the charges that I am going to mention happen to be of that kind. Right? That they do become black hole in some region of the moduli space, and then on the other hand, you can also count their number in some other region of the moduli space. Okay, and I'll write down the answer for both. So the charges that we are going to choose is q units of magnetic charge of B4 mu, one unit of Okay, so this is a system that it carries various amounts of. Pardon? Yeah, it is arbitrary because, as I said, we make the choice of charge in such a way that you can do the counting on the one hand, and on the other hand, there should be some part of the moduli space where it becomes a black hole. Yes. Why? Well, because you can count this, right? I think that's the only motivation. The point, many of these charge combinations are related to each other by duality, right? So when I wrote down one charge, it's also equivalent to many other combination of charges, right? But this doesn't cover all the charges, right? There are other charges which are not part of the same duality orbit, right? But it's more difficult to count. Right? So that's basically the reason for this choice, right? It's just practical consideration that unless you can count it, it's not very useful, right? You can calculate, you can find the black hole entropy, but there's nothing to compare it. Right? It just so happens that for these charges, one can count the number of states. Why not? Well, basically, you have to explore, right? You explore the various constituents, right? I mean, there's a hard and fast rule that hard and fast rule is this, that you should be able to calculate both sides, right? Then you have to explore what kind of system you can actually analyze and count states, right? And this is one system in which you can do this, right? It's basically purely practical consideration. That you find something where you can count and compare. And the point is that if you can find even one system where you can count and you can compare the black hole entropy, and if it doesn't agree, then that's a problem for the theory, right? So the idea is that you test many systems, as many systems as you can, and each of those provide a internal consistency check on the theory. Right? If any of them fail, then the theory fails.
So, any please explain to humans out the enhancer.
The yeah. So some charges are 1 unit. Okay. The others are arbitrary integers. So Q, N, and J are arbitrary integers. Q, N, J are arbitrary integers. Is that what you meant? Or okay. And then some charges are just 1, right? Here 1 unit of electric charge of B5 mu and 1 unit of magnetic charge of G4 mu. So you define the partition function. There are 3 variable charges. So you define a partition function of 3 variables Q1, Q2, Q3 as some omega. Okay. Omega will be a function of N, Q, and J. Q1 to the N, Q2 to the power Q, and Q3 to the power J. Okay. And the idea is that this is something that you can calculate. Okay, if Q1, Q2, Q3 is something that you can actually calculate and write down an explicit expression, okay, which is what I am going to do now.
One electric magnetic charge just to be value and
G formula.
is 0.
These are in some sense the 0-point charges, right? But okay, I mean, we'll not, yeah. So I mean, we need this, but it's not for this purpose. It is, you don't have to worry about this. So the result is that the 0-point charges will also see elsewhere is that if Q1, Q2, Q3 is given by Q1 inverse, Q2 inverse, Q3 inverse. These are the 0-point charges. These are the ones which have the form Q1 to the C1, Q2 to the C2, Q3 to the C3. Then product K, L, J, these are all integers. K and L are positive. J has no restriction. It can be positive or negative, except that if K and L are both 0, then J is only negative. Okay, that's the condition. So they are going to. So this is the formula. C's I have not told you so far. Okay, C's are arbitrary coefficients, but if I tell you C, then this formula tells you exactly what F is. Okay, and then you have to do this Fourier transform to extract what the actual numbers omegas are. These are the number of oscillators. If you remember, the bosonic oscillator had positive, negative coefficient here, and fermionic oscillators have positive, right? So this is exactly the structure that we found from the oscillators, right? Q1 to the N1, 0, Q to the N2, 0. That's exactly what the structure is. This is basically contain information about how many oscillators of each kind you have, right? Because each bosonic oscillator give you -1, each fermionic oscillator give you +1, right? So the C's are basically for given charges KLJ, the number of the difference between the number of bosonic oscillators and fermionic oscillators, right? That's what the C's are counted. Yeah, but the point is, okay, that's because the way I had written it, right? For any given power of Q, right, that Ri may or may not be there, right? That oscillator may or may not be there, right? So if the oscillator is not even there, then the power is 0, right? So here you are counting, you have fixed the charge, and they are asking how many oscillators are there, right? For each bosonic oscillator, you will get -1, right? So if there are say 10 bosonic oscillators, you will get -10, right? If there are 8 fermionic oscillators, you will get +8, right? And this result will be then -2. Okay, so this part is coming because you have product of many factors, right? Each of which may be the same, right? Each of which gives you 1 minus Q inverse, and hence you get 1 minus Q to the minus something. Is this clear? Okay, so this is the structure, and the C's, I'll just write down the expression for the C's and then maybe I'll stop. Okay, which C's are not very simple. So C's are known coefficients. Defined by the following relation. Okay, thetas are Jacobi functions. Theta mn are Jacobi theta functions. This also I'll write down explicitly in case you have not seen. So theta 0 0 Okay, so let me explain this formula. Okay, this is completely explicit, even though it's complicated. So the idea is the following: you first define these three functions, theta 0 0, theta 0 1, and theta 1 0. Okay, which are functions of two variables, tau and z, given here. Right, this n sum over n runs from minus infinity to infinity for all integers. So take these functions and construct this combination. Here is a function of tau and z. The claim is that this combination has an expansion of this form. You can expand this in powers of e to the 2 pi I n tau, e to the 2 pi I j z, and the coefficients of expansion is a function of this combination 4n minus j square, and it's some function that I am calling c of 4n minus j square. This function is what appears here. Okay. So the complication essentially is counting how many oscillators of each kind that you have, right? Because you see this part is simple. Now problem is here, right? This c, as we discussed, the exponent is just describing essentially the difference between the number of bosonic oscillators minus number of harmonic oscillators, right? Because every bosonic oscillator gives you -1, every harmonic oscillator gives you +1. So that difference of how many bosonic oscillators minus how many harmonic oscillators of each kind you have, okay, that calculation is done by this formula over here. But this formula is explicit enough that if you want to calculate, for example, omega n q j, right, say up to n q and j 10, right? Suppose you want to calculate omega n q j for all n q j up to 10. You can put this formula on the computer and evaluate it. Right? First, you have to carefully evaluate these coefficients, C, right, by doing this. And then once you have got the coefficients, you put it in this formula and then let it expand and get the result. So these are the 0-point charts, right? Because if you remember that a 0-point contribution was q to the c1, q1 to the c1, q to the c2, q3 to the c3. So these are the 0-point charts. Right? The vacuum carries, the ground state of the black hole carries these charges. Not considering arbitrary number. See, yeah, the point is the counting is more difficult. You could do the arbitrary number, right, but the counting becomes more difficult. That's all. Right? For some cases, the counting is known. For some cases, it's not known. Right? So not every state in this theory has been counted, right? But for those that have been counted, we can compare the black hole entropy. And maybe I'll just give the asymptotic expansion. For large NQJ, omega NQJ goes as 4 pi or 2 pi, I think. Sorry, pi times this one agrees with SPH. Right? You can calculate the Beckenstalk entropy independently by calculating the area of the event horizon of the corresponding black hole. You have to go to appropriate point in the moduli space where it is a black hole. Right? There you can calculate the Beckenstalk entropy, and this agrees with the Beckenstalk entropy. And then, of course, the challenge is that what about the corrections? Right? So this gives you a completely explicit expression, and you can evaluate it to arbitrary order. Right? However many orders in subleading expansion you want to calculate it, you can calculate it. Right? So this will have an expansion in powers of 1 over the charges, because this is valid for large values of Q1, N and J. Right? And then there will be terms which are lower powers of Q1, N and J. And the idea that can we reproduce each of those terms from the analysis of black holes. And it turns out that you can indeed reproduce those terms from the analysis of black holes. But first of all, you have to go beyond classical beyond two derivative actions of gravity, right? Because string theory has had derivative corrections to the gravitational action. You have to take those into account. And then you also have to take into account quantum effects, right? Just classical black hole analysis is not good enough. But once you start analyzing quantum fluctuations around the black hole, you can explain all of this correction. So all you don't know, but you have tested in many cases, right? And whatever has been tested, you can reproduce from the analysis of the black holes. Right? So the idea, so then the idea is that it not only teaches you how to reproduce the black hole entropy, but it also teaches you how to go beyond the leading order contribution to the black hole entropy, right? By taking into account the effect of higher derivative terms, the quantum corrections, and so on. Right? All that information is contained in this exact formula that we have here in the formula for F. Okay, so I think I'll stop.